Hey guys, and welcome to our second video of our second unit on the particulate nature of matter. Our first video focused on early models of the atom and looking at isotopes and mass spectrometry and how mass spectrometry was used to determine the existence of isotopes. So today we're going to get a little farther into our atomic models, going more into Bohr's model and how he figured out the existence of discrete energy levels, as well as the quantum mechanical model, the current model of the atom. And then at the very end, we're going to move up from the atomic level of matter up to a more macroscopic level. Okay, so to start with this, we're going to review the electromagnetic spectrum, which is included in your data booklet. I'm not sure if it's still section 3 or a different section, but it basically tells you that there are different levels of energy that are represented by different wavelengths and frequencies. The visible spectrum is only a small portion of the electromagnetic spectrum, and the wavelength and frequency of light are inversely proportional. So the longer the wavelength, the smaller the frequency, and the shorter the wavelength, the higher the frequency. And when you multiply wavelength and frequency of light, it equals the speed of light, which is also given in your data booklet. You can see here that gamma rays are the highest energy part of the electromagnetic spectrum, whereas radio waves are the lowest energy. So they have low frequencies and long wavelengths. Sorry, I had to move to my room. It was too loud in the living room, but anyways, so why do we care about energy in relationship to the atomic model? Well, it was this relationship that when electrons gain energy, they can move to different energy levels and then fall back down, and specific colors of light are going to be released whenever electrons move because there are discrete differences in the energy levels. So you can actually measure the difference in energy levels based on the wavelength of light emitted. So this is what allowed Bohr to really develop his model of the atom based on what Rutherford discovered about the nucleus, and the electrons are around the nucleus, but he didn't know that they were held in those specific energy levels until Bohr and his experimentation. So each element produces a unique emission spectrum. When those electrons are excited and they jump to higher energy levels and they fall back down, they release specific discrete colors. So this is called a line spectrum, which is, you can see these different lines here of color, as opposed to a continuous spectrum, which looks more like a rainbow of color. So this, for example, is the emission spectrum of Mercury, and these colors that we see here are a result of those electrons being excited and jumping to higher energy levels and then falling back down in different patterns in order to produce these lines. So each element will have a distinct and unique line spectra that represents it. And I do want to make it clear that there are a lot more emission lines both below the visible range and above the visible range. We just can't see them. We cannot see wavelengths higher than about I guess 700 nanometers, so longer than 700 nanometers, that goes more into the infrared region, and then below like 400 nanometers, that's too high of a frequency, that's ultraviolet light. We can't see that with our visible eye. So when I say line spectrum, I'm just talking about visible lines. So hydrogen produces other infrared spectra, like I said, that can't be seen with the naked eye, UV or infrared, but all spectra have these discrete visible lines, and you'll notice that they converge towards the high energy end of the spectrum. So these lines get closer together the higher in energy they get. So that means that the distance between the energy levels, the farther and farther away from the nucleus you get, the closer together they get, and that is also supported by this convergence data in the line spectrum. So we're going to go over the specific colors that are seen with the hydrogen in particular, and how they prove that hydrogen electron can only exist in certain fixed energy levels. Okay, so what I have here is a representation of energy levels represented by this n, quantum number n, that represents the energy levels. You can see 1, 2, 3, 4, 5. And if infinity right here represents when the electron has completely been removed from the atom, so it represents ionization energy. You can see here that when the electrons drop specific numbers of energy levels, they emit specific wavelengths of light. The only colors that we're able to see is when the electron falls from the 6th to the 2nd energy level, the 5th to the 2nd, the 4th to the 2nd, or the 3rd to the 2nd. Whenever electrons get excited, they don't necessarily have to fall back down to the 1st energy level. If they stop at the 2nd, that produces energies of wavelengths which we can see. So specifically, if you fall from the 6th to the 2nd energy level, that produces the highest energy jump, which we can see, which corresponds to the lowest wavelength, which is about 410 nanometers, which is violet. We can also see blue if it falls from the 5th to the 2nd energy level. We can see green if it falls from the 4th to the 2nd, or we can see red, which is the longest wavelength at 656 nanometers if it falls from the 3rd to the 2nd energy level. If you have anything greater than those jumps, that is in the UV region which we cannot see with our naked eye, and that includes the falling from the 2nd to the 1st energy level, because you can see that gap between energy levels 1 and 2 is much greater than between energy levels 2 and 3. And then anything smaller than that is going to result in too long of a wavelength for our eyes to see, so it results in the infrared region. So these specific regions that result in the falling of electrons between specific energy levels have different names. The ones that we can see and are called the Balmer series, so they represent the specific, red, green, blue, and violet lines. There is one more that can fall from the 7th to the 2nd energy level. It's like right here, right on the edge of what we're able to see, and normally it's not included in the hydrogen emission spectrum, which is why I have it in gray right here. But the higher energy levels, the ultraviolet series is called the Lyman series, and then we have 3 different series of infrared light, so it's too small of energy for us to see, the Passion, the Bracket, and the Fun series. You don't have to worry about that. You don't even have to worry about the names of these series. I just wanted to make it clear to you that they are discrete sets of energy transitions that have names. So how does this relate to Bohr's model? Well, Bohr designed a mathematical atomic model that explained these line spectra of different elements. He hypothesized that electrons existed at these specific energy levels, called principal energy levels, and then electrons farther away from the nucleus are in higher energy levels. He also said that electrons like to orbit the nucleus at their lowest possible energy levels. However, they can't absorb energy, become excited, and jump to the next highest energy level. He also hypothesized that there is no stopping between energy levels, which is why we only see discrete lines in the emission spectra. So therefore, energy levels are quantized, which means emissions of energy only occur in specific discrete amounts that we can measure. So because of that, you can see the different rings that he put representing energy levels outside of the nucleus of the atom. However, we know that Bohr's model is not completely accurate. The most current model of the atom is the quantum mechanical model. So it is the most recent and accurate model to date, in which there are 7 principal energy levels, which represented by the 7 rows of the periodic table, and 4 sublevels surrounding the nucleus. So he broke up those, well, not he, but the quantum mechanical model breaks up those energy levels into sublevels of different shapes, which describe the most likely location and position of an electron. So they have different shapes: s orbitals, p orbitals, d orbitals, and f orbitals. And each sublevel, this s, p, d, or f, have different numbers of orbitals in them. So the s sublevel only has 1 s orbital in it, whereas the p sublevel has 3 orbitals in it, the d sublevel has 5 orbitals in it, and the f sublevel has 7 orbitals in it. But we're going to review that in the next unit as well. So these orbitals are specific regions around the nucleus where an electrons can travel. They are probability locations rather than the electrons, orbiting the nucleus in rings. They're actually moving at very high speeds within a specific probability location. That is what an orbital is. And then we have these different orbitals that occur in the different principal energy levels, which is denoted by the 1, the 2, or the 3, 4, 5, 6, 7. So I wanted to give you a little bit more background information on this quantum mechanical model and how it was developed. So it started with de Broglie's hypothesis. So in the 1920s, there was a French physicist, his name was Louis de Broglie, and he hypothesized that since waves behave like particles, then particles could also behave like waves. So therefore, the Bohr model, which came previously, wasn't accurate for elements with more electrons, because Bohr only assumed the electrons acted like particles and not waves. So the particles those electrons could interact with each other, and his model did not account for that at all. And it also did not account for the wave-like nature of those electrons. So de Broglie's hypothesis said that all forms of matter act like waves, so electrons have duality of nature. They can act both as particles and waves. So that was the first step into the development of the quantum model. So then in 1926, Erwin Schrödinger, he used de Broglie's hypothesis to come up with what's called the Schrödinger equation, which led to the quantum mechanical model of the atom. So then Heisenberg added to this by coming up with his uncertainty principle, which says it's impossible to know both the energy and the exact position of an electron at the same time. That's because when you try to figure out the location of an electron, it actually changes its speed and location. So you can know one or the other, but not both at the same time, because trying to measure one affects the other. So this led to electron orbits actually being replaced by orbitals, which are again the probability locations. So it is through the combination of de Broglie, Schrödinger, and Heisenberg, all collectively their theories and their equations led to the current quantum mechanical model. So making a transition from looking at matter on an atomic level, we are going to look at it more on a macroscopic level. So looking at matter macroscopically, there are three different states: solid, liquid, and gas, and we already know this. Solids have fixed shapes and volumes. They can't be compressed. They have very strong attractive forces holding them together. However, the atoms are constantly moving and vibrating in fixed positions. If you add energy to that solid, it still has a fixed volume, but because of the additional input of kinetic energy, it no longer has a fixed shape. It takes on the shape of its container. It still cannot be compressed, but its forces between particles are weaker, allowing the particles to kind of flow over each other. And then finally, if you add more kinetic energy, then that liquid will turn into a gas with no fixed volume or shape. It can be compressed because it has very weak forces between the particles. And when we're talking about ideal gases, you assume that those forces are zero. So the particles are going to vibrate, rotate, and move in an X and Y fashion, so move in a translational manner, much faster than in a liquid. Then the fourth state of matter, plasma, that's when the matter has so much energy that gas actually becomes ionized. So the electrons kind of escape from the atom, and then that gas actually carries a charge, so that's plasma. So speaking of kinetic energy, the average energy of those particles in the three states of matter are represented by temperature. So this affects the way particles move. Of course, if you add more kinetic energy, then you are adding more movement to the particles, and the average kinetic energy is going to go up, so the temperature will go up. So temperature is just a representation of the average kinetic energy of the particles. And remember, in science, we use Celsius and Kelvin scales. We usually don't use Fahrenheit. And to switch between Kelvin and Celsius, you just have to add 273 to your value in Celsius, and you will get that value in Kelvin. So the lowest point on the Celsius scale is negative 273 degrees, which is corresponding to 0 Kelvin, known as absolute zero, a theoretical temperature at which all particles would stop moving. But you would see that the graduations in the Celsius and the Kelvin scale match each other. So a change in 1 degree Celsius is corresponding to a change in 1 Kelvin. So even though 0 degrees Celsius is the same as 273 Kelvin, so the freezing point of water, if you went to 1 degree Celsius, a change in 1 degree, that difference is going to be the same as the difference of Kelvin. So that would be 274 Kelvin, and 274 minus 273 is still 1. So the change in those scales is still going to be the same. So the last thing I wanted to talk about was changes of state. How does this kinetic energy represent the changes in states of matter? This is represented by what's called a heating curve. So this is something we did not talk about last year. So a heating curve represents how a change in energy reflects a change in temperature, because the more kinetic energy, the higher the average, or higher the temperature, because the average kinetic energy will get higher. So I want to show you how to interpret these heating curves. This one specifically is for water. So you can see here, if the energy input is 0, we don't have any temperature, obviously absolute 0. But as the energy goes up, and we get to 0 degrees Celsius, which is the freezing point of water, we see this flat area of the heating curve. So this actually represents the point at which the ice starts to melt. So this is called an equilibrium, because there is no change in temperature at this point. all the energy being put into the ice is being used to disrupt the crystal lattice and break those attractive forces within that solid ice. So even though we're adding energy, the temperature does not change, because as soon as we add that temperature, it's going towards breaking those bonds and it's not increasing the kinetic energy of those particles at that moment. So we're going to see a flat phase here, which is the equilibrium between melting and freezing. Then we continue to add energy, and now the water is in its liquid state. And when we reach 100 degrees Celsius, that is the point at which the water is going to turn into gas, into steam. So again, there's going to be a flat area here of equilibrium whenever no temperature change will occur, because all of the energy is being used to turn that liquid into a vapor. So the temperature does not change in this plateau phase. And then after that point, the gas can continue to rise in temperature because we're adding more and more energy to that gaseous water vapor. I also wanted to let you guys, remind you guys that melting and boiling are endothermic reactions. So that means energy has to be put into the substance for those phase changes to occur. In order to melt or to boil, you have to add energy. However, the opposite occurs whenever you freeze or condense water. So if you freeze water, it is an exothermic reaction because it's going from something with more energy to something with less energy. So that extra energy is released, and so that would be an exothermic reaction. All right, and that is it for our second video, and I will see you in class tomorrow. I hope you have a great rest of your weekend. Bye.